All right, you're welcome to these teachings or these lessons on the JAMB syllabus. Chemistry JAMB syllabus, to be precise, is what we are going to be looking at. And I want to start off by um, sharing with you um, or just giving you a rundown of what the JAMB syllabus entails and what we are going to be covering in the course of this class. So in the course of this class, we are going to be looking at the JAMB syllabus in detail. And I just want to show the JAMB syllabus and just give you a little rundown of what it is expected that we should cover within the scope of our of the chemistry syllabus for JAM. So first and foremost, we are supposed to look at separation. Um, we're supposed to look at separation. Sorry, just trying to bring up that screen. Okay. We're supposed to look at separation of mixtures and purification of chemical substance. I think, man, this So, like I was saying, we're supposed to look at the chemistry jam syllabus together. I'm going to be taking you teaching on the topics and the subtopics embedded in the jam syllabus. It promises to be a very wonderful, wonderful teaching section. So I want you to just stay glued and ensure that you keep coming to this page to check on the lessons as we go along. So let's quickly do a quick rundown of what the JAM syllabus entails or what we are supposed to cover with the JAM syllabus. I just want to do a share. Let me see if I can share my screen and show you what the syllabus looks like and what we are supposed to, what we are supposed to cover. First and foremost, we'll be looking at separation of mixtures and purification of chemical substance. And under this, we are going to be looking at the subtopics like pure and impure substance, elements, compounds and mixtures, chemical and physical changes. We're also going to be looking at chemical combination, which is the second topic we're going to be considering. And at this particular junction, we are supposed to look at Gay-Lussac's law, stoichiometry, law of definite and multiple proportions, law of conservation of matter, and so on and so forth. Then we jump into kinetic theory of matter and gas laws. And on that kinetic theory of matter and gas law, we're going to be looking at some interesting laws like the Boyle's law, the Charles law, the Graham and Dalton's law, and so on and so forth like that. And thereafter, we'll be looking at atomic structure and bonding. Atomic structure and bonding is another very interesting topic that we are going to be looking at in the course of this teaching. So under this, we have so many things to consider: chemical bonding, the periodic table, atomic structure, you know, and the shapes of simple molecules. That is talking about the linear, the non-linear, the tetrahedra, and so on and so forth like that. Then we jump into nuclear chemistry, of course, and a very, very interesting part of chemistry. We talk about radioactivity, nuclear reaction, talking about fission, fusion, simple equations, beta decay, gamma decay, and so on and so forth like that. So we're going to be looking at all that. Then we look at air, very, very important. Air is germane to life, and we look at the composition of air. We look at the noble gases, carbon dioxide, nitrogen dioxide, and so on and so forth. all the constituents of air. We're going to look at them one after the other. So then we'll look at water. Water is another very key thing that is important to life. So we look at water, composition by volume, water as a solvent, atmospheric gas dissolved in water, temporary permanent hardness of water and the examples and water crystallization and so on and so forth. So we're going to consider all these. Then we look at solubility, of course. And in solubility, we have some little calculations that we're going to be getting ourselves involved in. Don't worry, it's not going to be so tedious. I'm going to ensure that I break it down in such a way that you will understand it clearly. So we'll look at saturated, unsaturated solution, supersaturated, solution, and so on and so forth. We look at suspension, solvents, and the all works like that under solubility. So then we move into environmental pollution. One of the major things that we need to be very, very mindful of, especially in this our dispensation, is the way we treat our environment. And in environmental pollution, we'll be looking at specific pollution like air pollution, water pollution, soil pollution. What are the contaminants that get into the air that pollutes the air? What are the contaminants that get into our soil? How do we contribute as human, and how can we, to an extent, control this pollution? Because if you pollute the the world or the earth, it comes back to us. You pollute the water, you have to use that water for one reason or the other, and then you get, affected by the pollution that you have introduced into the soil. So we're going to be looking at pollution and environmental pollution. We consider it. It's going to be a very, very interesting topic again. Biodegradable, non-biodegradable pollutants, and so on and so forth. So we're going to be considering all these. Then we jump into acid, bases, and salt, of course. Acid, base, and salt. We look at what an acid is. We look at what a base is. We define them. We look at the examples, and then we touch on indicators. The different acid base indicator that we make use of, and then we talk about the different types of salt also, and we'll do a little qualitative comparison of conductances of molar solution of strong and weak acid and bases, and relationship between conductance and amount of ion present and their relative mobility. So these are some of the things that we're going to be looking at. We look at the pH scale, how to calculate the pH value, acid-base titration. We are going to be looking at all that, looking at how do we interpret graphical representation of the titration curve, and so on and so forth. And then we'll look at the 10th topic in the syllabus, which is oxidation and reduction. Here we'll look at what is an oxidant, what is a reductant, what is oxidation, what is reduction. We'll also be looking at how to balance the redox equation. We look at how to balance the redox equation. So these are some of the things that we're going to be delving into as we continue in this teaching on the JAMB Chemistry syllabus. So we now move into electrolysis, which is the 11th topic on the JAMB syllabus, and then we'll look at what is an electrolyte, what is a non-electrolyte. We'll look at the Faraday's law of electrolysis. We'll look at electrolysis of dilated H2SO4, copper sulfates, and so on and so forth like that. So it's going to be very, very interesting going through those topics too, and I can assure you that you will really have a good time with the teaching and the way I'm going to be explaining some of these concepts to you. So we look at electrolysis, we talk about the uses of electrolysis, electrolysis for purification, and we look at electrochemical cells, and so on and so forth. And then we move into the 12th topic, which is energy changes. And in looking at energy changes, we look at the entropy change, the enthalpy change, we're going to consider all these, and then we have certain maybe it's little calculations that we can use to explain or to buttress the topic as the case may be. So we also look at the 10th topic on the JAM syllabus, which is the rate of chemical reaction, the rate of chemical reaction. We'll look at these, and then we move on from there. We'll go to chemical equilibria. We'll consider the chemical equilibria, stage by stage, and we look at them subtopic by subtopic as we move along. Then we delve into the world of non-metals and their compounds. So we look at non-metals, we look at their compounds. What are the non-metals? What is the name of their family? Like the halogens, and so on and so forth. When we get there, we'll unflesh it, as in we'll expatiate and make it very much explicit as I go. This is just like an overview, and I don't want to spend so much time, with this, so that we can quickly move into the lesson proper. So we look at the nitrogen, the sulfur, of the non-metals, and so and carbon, and so on and so forth, because of the cycle, carbon cycle, the nitrogen cycle, and so on and so forth. So we now move into metals and their compounds. Consider the alkaline metal, the alkaline earth metals, and so on and so forth. Then we pick up the metals one after the other. We try to explain and give some of the characteristics of these metals and their peculiar reaction. Then we move into an aspect of chemistry that is also very, very important, which is organic compounds. Organic compounds, and this is a very sure question in the JAMB examination for chemistry. So we're going to be looking at the aliphatic hydrocarbon, talking about the alkanes, the alkynes, and so on and so forth. So we will also touch on the alkanols, the alkanals, the alkanones, alkanoic acid, and so on and so forth, like that. And so we also look at macromolecules that we call giant molecules, carbohydrate, proteins, and so on and so forth, like that. So this is about, basically, this is what we are going to be considering or covering in the course of our time together, as in me teaching you this aspect of chemistry. And I can assure you that you sure do have a very wonderful time in this lesson. So I'm going to quickly go forth to the first topic, and we'll look at what it entails. And the first topic, let me quickly share that slide with you. Let's see. Okay. Let's see the slide here. Okay. I think this is the slide I'm going to share. Okay. Start from the beginning. Permit me to quickly do this. Let's have a slideshow from the beginning. Okay. Oh, beautiful. So this is what we are going to be looking at together. And this is the first topic in chemistry. We want to explore pure substances, and we want to look at elements, compounds, and mixtures. Elements, compounds, and mixtures. My name is Anjoni Oluwafemi Excel. By the way, in case you don't know me, let me introduce myself. And I will be your teacher for the chemistry syllabus for JAM class, for JAM, the JAM chemistry syllabus. So I'm going to be looking at this topic one after the other, starting from the first topic that you can see on your screen. So I want to explore the pure substances, elements, compounds, and mixture. So I am Anjari Oluwafemi Excel one more time. I hold a BSc in chemistry, a postgraduate diploma, a postgraduate degree rather in science education, and a master's degree in environmental and analytical chemistry. Let's jump into the lesson proper. Now, for this lesson, we have the following objectives, or we have the following learning objectives for this particular lesson. By the end of this lesson, you should be able to distinguish between pure and impure substances. You should also be able to use the boiling point and the melting point as criteria for purity of chemical substance. You should also be able to distinguish between elements, compounds, and their mixtures. Equally, you should be able to differentiate between chemical and physical changes. And you must equally be able to, by the end of this lesson, identify the properties of the component of a mixture. Properties of a component of a mixture. Okay. All right. On to the next one, pure substances. I know you've heard about these before. It's not something that is strange. Probably you may not look at it from the perspective of chemistry, But when we talk about pure substances in chemistry, this is what it connotes. A pure substance consists of only one type of particle or component, such as an element or a compound. Now, these substances cannot be separated by physical process and exhibit consistent properties throughout. So a pure substance in the world of chemistry, in the realm of chemistry, simply means a substance that consists only one type of particle or component. An example of pure substances are elements and compounds. And examples of elements include oxygen, gold. Example of compound includes water and methane. So in nature, you can actually find elements like tin, diamond, sugar, is a compound, and then water, which virtually every one of us makes use of. So these are examples of pure substances, elements, and compound. And don't forget that a pure substance consists of only one type of particle or component, such as what an element or a compound. Okay, now moving along, let us try and understand that definition now. For us to understand that definition, I've put up some questions and asked. And I want you to just drop your comments, drop your answers in the comment section. I'll pick it up from there and then we'll review it. So, for me to really be sure that you understand this topic, how can you tell if a substance is pure or not? You can drop your response in the comment section. How can you think of an everyday example of a pure substance, and how do you know it is pure? Can you think of an everyday example of a pure substance, and how do you know that it is pure? So you can drop your response in the comment section. Also, what are some examples of pure substances in food and drink? So you can give me some examples. Well, I've shared one with you in the course of explaining or defining what a pure substance is. That's in the previous slide. So you can come up with others and just drop your response in the comment section. Also, if you mix two pure substances together, does it result in a pure substance? Why or why not? If I mix two pure substances together, let's take for instance, probably I'm mixing water and sugar together. Will I still have a pure substance? If it is so, why is it? If it is not, why not? The next one that I want to ask, and I want you to just drop your response also in the comment section, is if something is made up of only one type of atom, is it always a pure substance? Why or why not? Is just for me to establish that you understand the definition that I've put forward. So if you are able to respond appropriately to these questions that I've stated out here, then you can be rest assured that at least you understand the definition of what pure substances are. All right, now let's move along and take the notch further by looking at the characteristics of pure substances. What are some of the characteristics of pure substances? Number one, pure substances have what we call fixed compositions. They have fixed composition. They have fixed composition. That's the number one property or characteristics of pure substance. Another property of characteristics is that they have uniform properties. Their properties are not just distorted or just scattered anyhow. No, their properties are uniform. It's holistic. They are uniform in nature. Another characteristic of pure substance is that it cannot be separated by physical method. There's no physical method that it can use to separate a pure substance. Although chemists over time have developed other methods to separate, which is not physical anyway, but there are other methods that you can make use of to separate pure substances now, but not a physical method. You can't use a physical method to separate pure substance. And also, they have what we call definite melting and boiling point. Now, this is one characteristics that make us to test that we can use to test for the purity of pure substance. A pure substance have definite melting and boiling points. Take, for instance, a pure substance like water. It has a definite boiling point. It has a definite melting point. The definite boiling point of water is 100 degrees Celsius. And that is one of the ways that we test in the laboratory if a substance is pure or not. If it conforms and it has a definite boiling point and melting point, then definitely it is a pure substance. Also, the density of a pure substance remains constant under fixed condition. So if by adventure the pressure is kept constant, the density of a pure substance will remain constant. This property can help us to distinguish between pure substance and what and mixtures. So these are some of the characteristics of pure substance. And if you have any substance that you're trying to ascertain if it is a pure substance or not, and it checks with all of these characteristics that we have stated out here, then it is definitely a pure substance. Okay. All right. So one example of a pure substance, like we said, is or are elements. Element is an example of a pure substance. So what is an element now? An element basically is a pure substance that is made up of one type of atom. It is made up of what? One type of atom. It cannot be broken down by chemical or physical method or physical means. We have stated this. An example of elements, so many of them on the periodic table. We have over 100 elements on the periodic table, but some examples that I've been able to draw out from for you include oxygen, hydrogen, gold. You can give me all the examples in the comment section so I will know that you know your elements. So if you look at the right-hand corner of your screen, you discover some colorful balls. One is tagged elements, the other one compound, then the other one mixtures like that. Now, if you look at it closely for elements, one thing you'll notice is that it is made up of just one type of atom. Look at the green balls, just one. They're same. They're the same. The yellow, they're the same. Under the element section, that's what I'm looking at now. The blue, they are the same. The pink, they are the same. That shows you that it is made up of just one atom. Now, when you move to the compounds, it's a bit different. You can have a bond between a blue and a yellow, to form a compound. You can have a bond between a blue and a pink, two blue balls and a pink ball to form another compound like that. So it's a bit different from what you have in the element. And we're going to be talking about the compounds very soon and what they are and examples of compounds too. For mixture, it's a whole lot different from element and compound. You can see that there is no definite, attachment or fixed way in which the constituents are bonded. For elements, for compound, you can see that when you have a blue, you have a yellow, and it is bonded like that in a ratio 1 to 1. Then for the other one, you see the two blue and one pink bonded like that in the ratio 2 of blue to 1 pink like that. But if you look closely at the mixture, it is completely different. It is completely not the same. And you can see the pink bonding together. You can see the yellow balls bonding together with the blue balls, and it's just and it kind of it does not have a definite composition. That is one thing about the mixture. So let's move along now and let's consider. Okay, this is another slide just telling us about elements and compounds. So we have oxygen, hydrogen, nitrogen, and carbon as elements, and then you have nitrogen oxide, hydrogen, water, H2O, as compound, NO2, and then carbon dioxide as compounds there. So let's look at what a compound is. A compound consists of two or more different types of atoms that are chemically bonded together in fixed proportion. Now, this is where you must understand the difference between a compound and an element. Elements made up of just one atom. A compound consists of two or more different types of atoms that are chemically bonded in fixed proportion. And that's the key word there. They are chemically bonded and they are in fixed proportion. Now let's take a look at the right-hand side and look at those colorful balls by the right-hand side of your screen. One of the things that you'll notice there is that if you have nitrogen oxide, for nitrogen oxide, you have nitrogen bonding with oxygen in the ratio 1 to 1. Now, let's look at the other one, nitrogen dioxide. For nitrogen dioxide, you have nitrogen and oxygen also bonding together, but the ratio is different this time around. They are bonded in a ratio what? 1 nitrogen against 2 oxygen. That's one of the things that you notice for nitrogen dioxide. And you discover that it is they are bonded in a fixed proportion. They are not just bonding, haphazardly. No, they are bonded in a fixed proportion. And that's one peculiar thing about compound, and they are chemically bonded. So compounds can only be separated by chemical methods, and their properties are different from elements that they contain. What does that mean? If I have nitrogen and oxygen bonding together to form a compound, the properties of nitrogen oxide is different from the property of nitrogen or oxygen, that is the constituent or the constituent atom that formed nitrogen oxide. So it is completely different. So examples of compounds, we've mentioned them and we can see them on the screen: water, sodium chloride, nitrogen oxide, carbon dioxide, carbon dioxide, and so on and so forth like that. Okay, having said that, now let's look at mixtures now. A mixture, on the other hand, is a combination of two or more substances. It's a combination of what? Two or more substances that are not chemically bonded and can be separated by physical method. Now, this is where the difference lies, actually. If you look at your compound, they are chemically bonded. Yes, they're made up of two or more atoms, and they are chemically bonded in a fixed, proportion, in a definite proportion, fixed definite proportion, as the case may be. Now, for mixture, it is not like that. For mixture, it is made up of two or more substances, but these ones are not chemically bonded and they can be separated by physical method. And that's the difference between a mixture and a compound. One is chemically bonded in a definite composition or having definite composition. The other one, it is bonded but not, they are not chemically bonded and they can be separated by physical method. Now, we must also note that a mixture can be referred to as an impure substance. What are examples of mixtures? Examples like air, salt water, soil, vegetable soup. Can someone else tell me examples of mixtures that you know of? Yes, you can just put it in the comment section and I will review them from there. Thank you very much. So examples of mixture, like I said, air, salt water, soil, and then vegetable soup. And if you look at it closely, mixtures can also be classified or yes, they can be classified into two, or we have two types of mixtures. And what are the two types of mixtures that we have? One, we have what we call the homogeneous mixture, and then two, we have what we call the heterogeneous mixtures. So we have homogeneous mixtures and then heterogeneous mixtures. Homogeneous mixtures are basically mixtures that have uniform composition. They have uniform composition, whereas heterogeneous mixtures, on the other hand, have what we call non-uniform composition. Their composition is not uniform. Whereas for homogeneous mixture, their composition is uniform. We'll talk more about homogeneous and heterogeneous mixture with examples in the next slide. So let's look at it together now. All right, homogeneous and heterogeneous mixture. Now, a very good example of homogeneous mixture is your coffee. How many of us have taken coffee before? Yes, put your response in the comment section. Yes. If you have taken coffee before, you discover that coffee is a mixture. And why is it a mixture? It's a mixture of different components. For us to get coffee, we'll get, first and foremost, we get a coffee bean, which we'll most time crush and make into powder form. And after that, we'll now get our boiling water or hot water, as the case may be, and we pour it into the coffee. For those that like taking their coffee black, you can just decide to, just take it like that. For those that can take their coffee black, for those that rather put sugar and milk, you add sugar and milk, then you stir together. Now, when you stir together, what you have is what? A uniform composition. You have a mixture because you have water, you have the coffee bean, you have milk, you have sugar, you stir together, and it is uniform. The composition is actually very uniform. There's no distortion, there's no, different, things just showing forth in the mixture. No, it looks uniform, everything gels together, so to speak. So coffee is an example of a homogeneous mixture. Steel is another example of homogeneous mixture because when to make steel, you have to subject it to high temperature, and it's because of subjecting to high temperature, the component that makes steel, they just form what? A uniform composition. So that's an example of homogeneous mixture. An example of heterogeneous mixture is pizza. How many of us have taken pizza before? Yes, you can put it in the comment section. Yes, pizza. So pizza is an example of heterogeneous mixture. Why do we say pizza is an example of heterogeneous mixture? Now, the reason is basically because of the fact that for us to make a pizza, you need your cheese, you need your You may put your veggies, like some people don't put veggies, and so many other items that you just put, and they are not uniform, not in a uniform composition. They don't form a uniform composition. You mix together, and then you get your pizza out. Your chocolate chip cookie is another example of an heterogeneous mixture, because it is made up of different substances, that do not form what uniform composition. In different composition, the composition is not uniform, and that is why you have that as an heterogeneous mixture. So please come up with other examples of heterogeneous and homogeneous mixtures, and then put them in the comment section, and I will look at them and review them accordingly. So having said this, now let's summarize between elements, compounds, and mixture. We just want to do a summary of key differences between the elements, the compound, and then the mixtures. Now, for the elements, let's summarize based on composition. Now, element is made up of one type of atom. We've said that before. Now, looking at compound, it is made up of two or more types of atoms that are bonded, chemically bonded together. Now, for mixtures, they are made up of two or more substances that are mixed together. They are made up of two or more substances that are what? Mixed together. In terms of separation, let's differentiate in terms of separation now. Now, elements cannot be separated by physical methods, but we said for compounds, they can only be separated by chemical methods. So we can deploy some chemical methods to separate our compound, but you may not be able to use a physical method to separate the compound. Now, for mixtures on the other hand, they can be separated by physical method. Physical method like filtration, physical method like decantation, and so on and so forth can be used to separate mixtures. And we are going to be looking at some of the separation method, as we go along in this class, in this teaching. So another way we can differentiate between these three elements, compound, and mixture is based on their properties. Elements have what we call unique and fixed properties. For compound, their properties are different from their elements. That's I've explained that earlier. For mixtures, components retain their properties. They just retain their properties in the mixture, so to speak. So examples of mixed examples based on examples, so we can also differentiate them. We have elements as oxygen, gold, and so on and so forth. For the compound, you have like water, sodium chloride. For mixtures, you have air, salt water, soil, and so on and so forth like that. Now, based on proportion of components, so you can also differentiate elements, compounds, and mixtures too. So based on proportion of components, we have for element, they have fixed composition, just one element, only one element with fixed composition. Then you have for compound, they have fixed ratio of elements, like I was explaining with nitrogen and oxygen when they bond together. And you can form nitrogen oxide, or we can form nitrogen dioxide, as the case may be, and it has fixed ratio of the element. For one, it will be 1 to ratio 1, it will be a ratio 1 to 2, as the case may be. Now, for mixtures, on the other hand, the components can vary in proportion. They don't have a fixed ratio in the proportion of the component that makes them up. And so these are key differences between elements, compounds, and mixtures. So I hope we are getting the lesson. So if you are getting it, so just say, just type in the comments, I am following, sir. I've decided to just give you an overview of what a substance is. Substances can be divided into pure substances and impure substances. Now, for pure substances, we can have what? Elements, we can have compounds. And for elements, we can have what? Metals, non-metals, metalloids, and then the noble gases, just like the element that we have on our periodic table and their differentiation in the periodic table. We are also going to be looking at this as we proceed along in this course of this teaching. So just stay tuned, and you get it as we go along. For impure substances, you have mixtures, and mixtures can either be homogeneous, just like we said earlier, or heterogeneous. We've made mention of it, and we have also given example to the effect. All righty. Okay. Now, having said that, let's talk about physical and chemical changes now. Physical changes, chemical changes, what are they? Now, physical change are changes that occur in which no new substances are formed and they are often reversible. Physical changes are often reversible and no new substances are formed. Now, for chemical change, on the other hand, there are changes that occur in which new substances are formed. New substances are formed and they are not usually reversible. Their new substances are formed, they're not usually reversible. Now, let's look at some example of physical change and chemical change for us to be able to concretize knowledge and understand this concept better. So examples of these changes now, for physical change, an example is melting of ice. When ice melts, what we have is just the corresponding water that froze up to become ice. That is, there's no new substance that is formed. It is just the water that was frozen that will defreeze, and then you have water. And it was water that we used in forming the ice initially. So no new substance is formed, and it is pretty what reversible because you can still take that water and put it back in a very low temperature, and then it will freeze back and become ice. Boiling water is an example of physical change also. Cutting diamonds, crushing a pencil, these are all examples of physical changes. And then we look at chemical changes now. For chemical changes, don't forget that we said a new substance is formed and then it is not reversible. An example is rusting iron. When iron rusts, it's a new substance that is formed and it is not reversible. It is not reversible. In fact, if you leave the iron to rust for so long, if you leave it to the element and it allow it to rust for so long, it can even become so brittle that even merely touching it, it will break off. So a new substance is formed, it is not reversible. So you cannot get the iron back. That's just it. Burning wood. When you get wood and you burn wood, it gives us ashes and probably charcoal or thereabout. Now, it's a new substance that has been formed, completely different from what we had before, and it is not reversible. You cannot get your wood back after you have set it on fire. Burning paper and so on and so forth. These are examples of physical and chemical changes. Okay, at this junction, I want to just summarize some of the key points that we've touched on in the course of this lesson. First and foremost, we talked about pure substances, and we said pure substances include elements, compounds. These are pure substances. We define what elements is or what elements are. We also define compound. We gave examples to the effects, telling us examples of element, examples of compounds. And then we move further by looking at mixtures. We define what mixtures are. And I try to establish the difference between mixtures, elements, and then the compounds. So we said mixtures can be classified into homogeneous and heterogeneous mixtures. I told you what homogeneous mixture is and what an heterogeneous mixture is, okay? Then we now move along. We talked about the physical change and the chemical change. We define what the physical change is, and we define what the chemical change is. And I also give corresponding examples, to buttress the definition. So if you have any question based on what I have taught so far, please just drop it in the comment section, and then I'll pick it up and do the needful, respond to them appropriately. But notwithstanding, I would like to evaluate this lesson by using this following question, and I would like you to also give me the response by dropping your answers in the comment section. So we look at this. Can you explain the difference between a pure substance and a mixture? Mhm. Why is it important to know if a substance is pure or a mixture? How do the properties of pure substances differ from those of mixtures? If you eat a pure substance, what changes might you observe? Why do chemists need to use pure substances in experiments? Can you think of an everyday example of a pure substance? How do you know it is pure? So all those questions, I want you to go through them one after the other, especially once you get the slide, go through them one after the other and ensure that you respond appropriately to them. I'll review them and then we'll pick it up from there. So these are some of the other questions I've also put together, so you can just provide answers to them. Which of the following is a chemical chain? Painting a wall blue, a bicycle rusting, ice cream melting, scratching a key across the desk, making a sandcastle. So you tell me what it is. You can drop your response or the answer in the comment section. Okay, all right. So with this, I've come to the end of this class, and thank you for listening. I would like you to please drop your questions if you have any. Drop them in the comment section. I'll pick them up and review them accordingly and respond to them appropriately. So thank you once again for listening, and thank you for joining the class today. I'll see you in the next class. Bye for now.